All right. All right. This is second installment of code walkthrough for BlueStore. Last time, which is I guess a month ago already, 2 weeks, something. We covered. What did we cover?
Went through the on-disk and in-memory data structures.
Right. Okay. Yeah, we talked about shards, the on-disk structure. Did we talk about the cache?
Don't think we went through the cache now.
All right. Okay. Let's share my screen. All right. You see that okay?
Yeah.
Or need a all right. .h. All right, let's start in the header file. For all the perf counters. You'll probably start by just walking through some of this. So class BlueStore obviously implements object store, big observers, handle config changes. These are a bunch of helpers that are called on startup and if config options change. So they take the config settings for checksums and compression and so on, and then initialize various in-memory structures onto that. Like that compression, for example, gets a handle for a compressor, and it figures out the blob sizes based on the mins and maxes and some other random stuff. The trans context is for declaration of a class that tracks a write that's being assembled, a transaction, and that's being committed to disk. We'll get to that shortly. That's sort of a key piece of the write path. This is used for reads. Buffer space is used for the cache. Collection is a collection. AIO context just tracks AIOs in flight. Okay, so the first meaningful class here is a buffer. This is for the in-memory buffer cache when we're caching data that object data that would be stored on disk. It has a few states. It's either empty, clean, or it's in the process of being written. It's never dirty but not being written because we never do write back. Every time we do a write, we always immediately queue it for disk. So it's a little different than like a traditional page cache or something. There is one flag that basically indicates whether this buffer should be expired as soon as it commits to disk, because sometimes we're operating in a mode where we want to cache writes after they're completed in memory until they fall off the LRU. And other times we don't want to cache writes unless we're explicitly hinted by the client. And in that case, we still have to keep it in memory while it's being in flight to disk in case there's a read or we need to pipeline a second write. But as soon as it's actually committed, then we throw it out. So that's what that flag is for. And there's some, they exist in an LRU. There's also lists by state, so we can identify all the writing buffers easily. There's a bunch of helpers for data it's in, truncating data off the end, maybe reallocating the buffer list so it's one buffer. Nothing terribly crazy. Buffer space is sort of the next level up in the cache. This is for a single object. It's a mapping of a bunch of file offset or object offsets to buffers. So in the Linux kernel, it'd be an address space, I guess, would be the analogous mapping. So it has a map of buffers here, which is an intrusive red-black tree. Actually, no, it's just a regular STL map of offset to buffer. And there's some helpers for adding buffers, removing them, speaking to a particular position and so on, doing discard, writes, reads, and so on. These implementations are a little bit tricky because there's this indirection for the cache that contains the buffer space, which I'll get to in a minute. And then the other sort of interesting thing here that's going on is, so a write would write into a buffer space. It would create a new buffer with the data at a particular offset, it would sort of discard anything that's previously existed there and then add the new buffer in. Finish write is called after that actually hits disk to sort of move it from the writing state to the clean state. Did read is sort of the analogous thing. After we perform a read off of disk, we will populate the data into the buffer cache. The flags are appropriately set. We're going to buffer reads. Those helpers are for. Shared blobs are something we talked about.
Sorry, Jay's just going back to the cache for a second.
Oh yeah, sure, yeah. Maybe we should jump to that. Good.
This reminds me a lot of the object cacher in that looks like it's has a single lock and is accounting for space used based on the memory allocated within every single buffer. Is that right? Rather than trying to have like one giant block memory that it's putting buffers in.
Yep. So I think the difference is that it's actually not the entire cache; it's a shard of the cache. So the way that it's structured in BlueStore, there's some number of shards on the OSD's opwork queue, like 5 or something, or 8. I can't remember what it is by default. Depends on if it's hard disk or SSD. BlueStore sets up the same number of shards, and the idea is that you tend to be on the same CPU. It's always the same work queue. Each work queue is working with PGs that are on the same shard. And so the collections within BlueStore are assigned to cache shards. And so all the locking is local to that shard, and hopefully there's some affinity between the memory and the cores that are actually doing that work.
Okay.
So there's generally no contention on those the locks for the cache at all, except when it's doing things like checking stats for trimming. There's a background thread that periodically will wake up and trim stuff, and that goes through and takes the lock on each shard in turn. Right. So the cache is an abstract sort of container. So it does a few things. It's got a lock and some counters associated with it. I think these are atomic just so that we can read them without taking the lock. But you generally don't. You're always holding the lock when you're modifying the cache, so it's not needed for the writes. But you'll notice that all these methods are all virtual. It's because there are 2 implementations of cache. There's an LRU cache, which is the first one, which is just a very simple LRU. When you add things, they either get added at the bottom or the top. And when you touch an item, it gets moved to the top. So there's a method, touch onode and touch buffer. They're basically two types of data structures that the cache manages, onodes and buffers. And they're sort of managed mostly independently, except when we're trying to do space accounting. A little bit wonky, but you'll see basically parallel sets of methods for add, remove, and touch for those 2 different types of structures. And then there's a trim, where you pass in the maxes and it'll just kick all the things off the end. And then the second implementation is 2Q, which is based on a paper 2Q caching algorithm. It's basically 2 LRUs. And when things fall off the first LRU, there's like a mirror list that has just as many items, but it's just the name of the item that got kicked off. And if you fault something back into the cache that was previously evicted, that's on that second list, it goes on to the higher priority part of the queue, and so it sticks around for much longer. It's very harder to get rid of. So in order for something to get into it's going to stay in the cache, it has to be added to the cache, get evicted once, and then get faulted back in, and then it's going to stick for a really long time. That's basically how 2Q works. So there's a hot list and a warm in and warm out. And they have really funny names in the paper, so that the names in the code don't quite match because the paper names don't make any sense to me intuitively. But yes, implement the same methods, but it's a little bit more complicated about how things get faulted in and whatever. Right, so that's the cache. So that's why this class over here, buffer space, these implementations are weird because they have various hooks into the cache to add the buffer, all these audit calls. Audit is basically a debug method that just traverses the whole structure to make sure everything is in sync. So it compiles out, and in normal builds, I think you have to find something to turn it on. Right, so those are buffers. You'll remember from last time, the sort of the on-disk data structure. You have onodes, which represent objects, and the data portions of onodes are mapped to blobs, which is basically just like a hunk of data that's stored, not even necessarily in one extent, but it's sort of treated the same. The metadata is managed together. It's got all the checksums and how it's compressed and the metadata about that data on disk, basically. Because we can clone objects, sometimes blobs are referenced by multiple objects. And so when that happens, there's a shared blob that's actually stored on disk that keeps track of the reference counts on those extents. In memory, that's also true, but it's slightly different in memory because the cache, the in-memory cache is always associated with the shared blob structure. So any blob that's ever instantiated in memory has a shared blob, a second allocation that's a shared blob, and the cache, the buffer space, caching the buffers is attached to that. So you'll see here, there's a shared blob. It belongs to a collection. It belongs, I think there's probably a cache pointer on here. I guess not. The collection is mapped to a cache shard. It has some flags to indicate whether it's the state for that shared blob is loaded into memory or not, and if it actually has any persistent state. Most of the time, objects aren't cloned, and so these are both false because there isn't actually a persistent instantiation of that shared blob. It's not shared at all, it's just the blob. It's just basically a container for the buffer space. But when it is shared, then nothing changes. You still have the buffer's memory associated with that shared structure. Hopefully that makes sense. It's a little convoluted. So there's they have a shared blob ID, a unique identifier for the shared blob that only is defined if it's loaded or if it's persistent. If it's not persistent, then I think this doesn't even return anything valid, undefined value. We track references on it, so there's some helpers here. But mostly you can just think of shared blob as a container for the buffer space in memory buffers. And there's a pointer to the on-disk state when it exists. The shared blob set is sort of the more tricky mapping that lets you actually find these. So most of the time when you load a blob into memory, you just, the onode has a flag that indicates whether the blob is shared, which is part of the blob flags field. So if it's not shared, then it just creates a shared blob and uses the buffer space attached to it. And that's it. But if that flag is set on the blob, then the shared blob actually has a persistent thing. And when it allocates the shared blob, it also registers it with the shared blob set because it'll have an ID associated with it. So I think if we look at BlueStore types and we look at BlueStore blob T, notice here there's this is the flag that says that the blob is shared. And when that's set, there is a field in here somewhere that indicates what the ID is. Share blob ID. I can't remember where it is. This is what happens when you don't prepare. Anyway, if it is actually shared, then it'll register with the shared blob set, and it's basically just a hash table of the shared blob ID to the shared blob pointer. And what happens because as soon as the blob becomes shared, because you clone it, it becomes immutable. And so we basically just copy the blob metadata to the target object. And so there's 2 copies of the blob with all the extents and the flags and everything in both objects. And then we aren't allowed to change them. The only thing that ever changes are the references, whether we're actually using the data represented by those blobs, and that's the part that's stored in the shared blob, the combined shared blob structure. So here you'll see it has a reference count map in that shared on disk structure. So anyway, there's a lookup function, there's an add and a remove. Oops, I'm going too fast. But this is slightly tricky because you have cases where the reference counts go away for the shared blob, and so then you have to deregister it from the shared blob set. So you can only look up if the reference count is still non-zero. So sort of lazily, you have to take a lock to remove it from this set. And yeah, that's about it. Blobs are here. So every blob that's in memory has a reference to the shared blob. So it's always there. Oh no, sorry, it's not always there. I think it's always there. I can't remember. To look at it. And yep, it's got a bunch of helper functions to determine whether it can be split into pieces because you're right in the middle of it. You can take references to pieces of it, all kinds of stuff in the memory blob. And I think did we talk about this before? We talked about extents and blobs, I believe, before.
Yeah, I think so.
All right. Yeah, or at least the on-disk part. So extents are basically maps. So you have extents, you have an O-node, you have a collection which has a map to O-nodes. O-nodes, each O-node has an extent map, which maps regions to blobs. Each blob will point to the shared blob. Possibly multiple objects will point at that if they clones. Those blobs, the shared blob will point to buffers owned by the cache shard. Similarly, all the O-nodes will also be owned by a particular cache shard. Most of the time, all the stuff lines up with the shards. The blobs, when you clone an object, you're always cloning to an object that has the same hash ID, so it always lives in the same shard in the same collection. So things sort of never move around in the namespace. And PGs belong in their entirety belong to one shard. So the only time that gets weird is when you split a PG. It might be that one of the halves or children or whatever of that split belongs to a different shard. So there's one sort of annoying bit of code in BlueStore here in split collection that might have to move a bunch of data structures to a different shard. And that is here, collection split cache. And it basically locks both cache shards, the nifty helper that gets the lock ordering right. And then it basically iterates through all the O-nodes, decides which shard it belongs to, and if it belongs to another one, then it removes it from one cache shard and adds it to the other cache shard. And it moves it to the destination collections O-node map, because the O-node lookup hash tables are per collection, so that they're sort of localized and the hash tables are smaller. And then it also has to move the shared blobs, buffers, and all this stuff, whatever. So there's all this moving stuff here. All that stuff straight. So I think that's most of it. So just a quick example, if you do get O-node, now let's do vault range. If we load a region of an object of the extent map into memory, then we're loading all the blobs. So this will hold on. All right, let me restart BlueJeans. Chrome sent a notification and that decided to break screen sharing. Right, share screen, window, there we go. All right, so it'll load up a bunch of decode sum. This decodes a shard that comes out of the key value database, a shard of an O node or of the extent map. And in here, we have a whole bunch of blobs that are sort of encoded. That's a really annoying and clever way to try to make them compact and also reasonably fast to decode. So this code is kind of convoluted. That's why I couldn't find that shared blob ID, because it's sort of encoded in line in this wonky format, only if it's a shared blob. But basically, if there's a blob ID, shared blob, then oh no, sorry, if it's, yeah, this is a different blob ID. But basically, if we get down here, if it's a shared blob, then we have to open the shared blob, which is another helper function. And shared blob. That will, in the general case, the common case where the blob isn't shared, it just creates a shared blob and is done. But if it is shared, then we first try to look it up. If we already had it, then great. If we didn't, then we create it and we register it. So that's the basic thing. The interesting thing here is that when you load the blobs, you don't actually load the shared blob necessarily, because it's actually a different key value. And the only thing that it stores is the ref counts on the extents. So if you're just reading an object, you don't care what other clones are also referencing those same bytes. The blob itself has enough metadata to read the extents, and we have the checksums in both objects. And so it doesn't matter. The only time you actually have to load the shared blob is if you're modifying the object and you have to change the reference count, which is nice, because that only happens in the right path. But assuming you do have to load it, then you go and you actually get the key out of the database. You set loaded to true, you load this persistent, allocate this persistent shared blob T, which is sort of the on-disk structure in memory, and decode it. Make shared blob is used in the case where you're cloning an object. So initially the blob isn't shared, obviously, but you clone it, then you have to make all the blobs that are not shared yet shared. And so it marks them dirty, sets the shared flag, allocates this persistent object, and sort of initializes the reference counts for the two objects that'll initially be referencing it, or maybe just the first one. And then when the actual clone does it. There is some code in BlueStore to try to unshare blobs, because it's erasure coded sort of write workload patterns. We make a clone of the object before we do an erasure code overwrite so we can roll back. And so there's sort of this kludge in BlueStore to try to like clean that up, so that we don't end up littering every object with all these shared blobs. And so that's what the make blob unshared is. It's a set of heuristics that work most of the time unless you have sort of a weird workload pattern. So it's good enough. But this is just the opposite, right? It unregisters it, that's loaded to false, deletes the persistent thing, and sort of deinitializes, backs out and undoes what the make blob shared does. All right, so let's go. We looked a little bit at read before. Should we look at that again, or should we let's look at the right one. The right one is actually right's where all the complexity is, so let's just get right to it. So everything in the object store layer goes through queue transactions. So the sort of the single entry point. When you call it, we collect all the contexts, deletions onto lists. This is for debugging, where we're sort of pretending that we're throwing away IOs. You get a reference to, or get a pointer to the collection and the sequencer. These map one-to-one, but that's a different in-memory structure because it survives in collections of the same name. But the main thing here is that we create a trans context. So this is the data structure that tracks data associated with a in-flight transaction. There it is. It's a child of AIO context because it initiates AIOs and it has a completion callback that gets called on it by the block layer. It's got a whole bunch of states that it works its way through in the process of actually doing the write. The prepare is what happens initially. We might be waiting for the initial writes. Once those are all done, then we queue the actual key value transaction to RocksDB that actually commits the operation. And then if there was deferred IO, like we journaled, then intent to overwrite data or something, then we also work through these other states that actually do that follow-up IO at the end, and then finish and clean up. Bunch of helpers for tracking latency and so on. It's associated with the collection and it's sequenced inside the sequencer. So the sequencer has an ordered intrusive list of the transactions that are in flight. And so this is our handle, our whatever node in that list. Each transaction has a cost associated with it related to the number of things we're doing and how many bytes we're writing. These fields track which O-nodes are being modified, which objects are being modified. Shared blobs are being modified or being written. Completions to finish, collections that got deleted that need to be mopped up at the end. This is usually empty, obviously. If there's deferred work, then this is we're in another list of deferred IO that has to happen, and so this is our position there. What blocks on disk were either allocated or released as part of this transaction, and the delta for our stats. So BlueStore is maintaining transactionally with each update a count of like the number of bytes of different types and a bunch of stats for like how many bytes are compressed, how many are uncompressed, how many are allocated, not allocated, yada yada. That roll up and eventually populate the StatFS output. So this is whatever delta this is incurred by this transaction. The IO context is the IOs that will be initiated as part of it. There's a sequence number that's sort of local to the sequencer. So there's just a numeric ID that increments every time there's a new transaction on the sequencer or within the collection. These keep track of NIDs and blob IDs that we used. There's a little bit of cleverness here to make sure they're unique, but and we don't, yeah, it's not really worth getting into, but NID is a unique name ID for an O-node, if I remember correctly, and blob ID for a shared blob. Few helpers here. So in some code, if we dirty the O-node, then we call this and just make sure that the O-node is on the dirty list. Yeah, that's mostly it. Trans context. So anyway, okay. So when you do a transaction, we create the trans context, and we can look here for txt create, and basically all it does is it allocates it. It gets a handle to the current RocksDB or key value DB transaction that is being assembled. So lots of, if you have a sequence of transactions, they'll all be pointing to the same transaction and sort of piling on their work on top of it until you eventually commit the batch. And then this basically adds it to the sequencer's list of transactions that are in flight. And then we call this add transaction. This basically takes the context of the transaction that the OSD passed down and sort of does all the work of figuring out what key value updates are happening, what IO, whatever. This is where everything actually happens. I'll get to that in a second. It also calculates the cost. So this is the number of bytes that we've done. We calculate a cost associated with the transaction. That's sort of a function of the bytes and the number of ops that's used for the throttling. We take any O-nodes that were dirty and we write them by basically putting them in the key value transaction so they're ready to go. If there's any deferred work, deferred IO, we encode those keys also. And then finalize sort of, let's go through these in order though. So the main one is txt add transaction. That's where everything exciting happens. So we try to be a little bit efficient here by getting all the references to the collections that are used in this transaction. Usually they're only like 2 or 1. It's just the actual collection and maybe the meta collection. Usually it's just 1. And then we iterate over the operations. So no apps don't do anything. They're sort of grouped here. So things that operate on collections, may or may not, collection may or may not exist right here. We have like a reference to the collection reference. So things like remove and create collection happen here. All the collection stuff is piled in here. And then they're grouped down below. There's a bunch of them that implicitly create objects. So these might happen. We set this to true. And then we actually look up the onode. And if the onode doesn't exist, but this is an op that creates it, then we'll actually create. Otherwise, we'll return unoint and actually usually error out. At this level, we basically are never supposed to hit an error. OSD is supposed to prepare well-formed transactions against the store. So this, so get onode will either look up an onode, or if the second argument is true, then it'll also create a new onode for a new object. So for these operations, we'll always get an onode back. It just might be empty. And for other ones, it might be a null reference. So these things like touch and write, all are getting a nice clean pointer to the collection and to the object and the arguments that are actually going to do the operation. So the interesting one is, let's look at touch. That's probably the simplest one, just to see what it does. Here, we already got an onode, right? Because get onode allocated one because the create flag was true. So all we have to do is make sure that there's a unique identifier assigned to that object, an NID, sort of like an inode number. And then we mark in the transaction that we should write the onode because it's been modified. And that's it. So if this was a really simple transaction and that's all it was doing, if it was doing a touch, then this would finish. We would calculate the cost. It'd be very small because there's like 1 op and no bytes. And then we would do write txt write nodes, which basically just goes through the dirtied items in that trans context structure and updates the key value records for them. So for all the onodes that are referenced, we do record onode. That do. It will reshard the extent map if it needs to be updated. It will basically figures out whether it needs to reshard the onode. And then assuming it gets all past all that, it will encode the onode into an in-memory buffer. So it's either inline BL, no, that's the extent map. Anyway, yeah, down here, it'll encode the onode into its key, possibly also the extent maps records keys that are also changed. And then it will set that key in the transaction that's going to be passed to RocksDB. Spit out some stats about how the onode is being written. Sometimes we modify objects, but we didn't affect the onode. I can't remember why that happens. But we have to keep track of those too. If we modify the shared blobs, then we need to go and get the key. If we deleted the shared blob, we have to delete the key. If we modified it, then we have to encode it into buffer and write that into the transaction. So that's basically it. Write nodes either updates the onode and or the shared blobs that are affected by that transaction. And then after we do all that, txt finalize KV. This is the last step. It basically prepares, it looks at all the extents that were allocated or released, and it, if there's overlap, it tries to, if you release something and then reallocate it, we don't want to actually update it twice. So it figures out what that overlap is. And then it calls into the free list manager for the allocate and releases. And it passes in the key value transaction. And in our case, the only implementation here is the bitmap-based free list on disk, which is basically doing merge operations with bit fields for all the blocks that are allocated or deallocated. So they're XORing the bits and the keys for the blocks that we either allocated or deallocated. And the reason why we do that is because sometimes we're preparing this transaction right here, but as you'll see in a second, it might not actually be given to RocksDB until later because we might have to wait for I/O to happen first. And so the ordering of the allocations and deallocations might switch around before it actually finally reaches RocksDB. And the merge operations are commutative or associative or whatever, commutative, I guess, because they're just XORs a bit. Okay, so that's finalize. Could probably be named like finalize allocation changes or whatever. There's some throttling here that slows it down. Probably this is going to go away once we are throttling at a higher level on the OSD with the new QoS stuff, but until then, this is where the throttling happens. So queue transactions will actually block sometimes. And then finally, we get down to this thing where it's process this TXT state proc. So remember the trans context had those like 12 states. It's basically a simple state machine that goes, I think, always in order. Sometimes it jumps back. But this just TXT state proc basically works its way through those states. So in the prepare state, which is what it started as, key transaction creates a transaction up here. TXT create starts out in the prepare state where everything starts. If there are no pending IOs, then we go all the way to AI await, saying that we're, or no, if it does have pending IOs, we say we're waiting for those AIOs, and we call this function here that actually queues those IOs for the kernel device. If not, then we jump all the way down. We're already in AI await, and we say that we're done with finish IO. Sort of the analogous thing here is that if I can't remember what the name of the function is, but if the block layer finishes the IO, it triggers a callback back into the BlueStore code, and it calls TXT state proc on the affected transaction. And so it'll call into right here. It'll be in the AI await state, and then it'll also say finish IO. So they both end up in the same place. And when that happens, finish IO basically says, okay, we're done with our IO, and so we switch to the IO done state and update some accounting. But the trick here is that say you had two transactions, A and B, and they both started some IOs. A came first, B came second, but say B's IOs finished before A's do. So B will be in the IO done state, but the transaction ahead of it is still in the IO wait state. And so this basically, so we can't actually do anything when B's IOs finish. We still have to wait for A to finish first. And so this update updates us, and then we basically start at the front of the list and we look for things that have finished IO. And then if they are done, if A is done, then it looks at as many transactions as are done and it finishes them all. So we basically loop. So we're starting at the front, all the transactions who are in IO done state, we process them in order. And this is the thing that ensures that even though IOs happen out of order, we still commit them in order at the end. So that means that we're calling back into state proc with IO done down here. This assert, we already have the queue locked here. The locking on the sequencer is a little bit wonky, but basically it's a lock that protects this list of the transactions. Again, these locks are almost never contended because we're always doing this in the same thread. So it's pretty rare that you actually are blocking in the mutex, but they're needed for a few unusual cases. So then we change our state to KV queued, which means they're queued to actually be committed to the key value database. This is where things start to get clever. Normally, this is false. Normally, we go into the queued state and we basically just get put on a list of KV queue of all the transactions that are ready to be committed. And then we wake up the KV sync thread to go commit them. There are a bunch of optimizations here that we've played around with that basically, for certain cases, the transaction can be committed synchronously. So you might have, 8 threads in the OSD that are processing these transactions, and they could all be queuing directly to RocksDB from those worker threads. When that's the case, then you can get somewhat better performance. But there are a bunch of you can only do that when there are no ordering issues with the IOs and a whole bunch of complicated conditions. So there's a subset here, you'll notice. If we want to do it synchronously, then it can't have allocated a new ID because we have to update a key that has the max. It has to be, if the previous one is already going through the key value thread, then we have to continue going through the key value thread, or else we'll sort of jump ahead of it in order. If there's unstable IO with other transactions, then we can't jump ahead, whatever. But if we get lucky, then we can do it directly. And we jump straight to submitted and we call it applied. But usually that doesn't happen. So we'll also ignore that. So most of the time you get put on the KV queue, and then there's another thread, KV sync thread, that you'll hear Mark talk about all the time because this is what does most of the work. Maybe not most of the work, a lot of the work in BlueStore. This is KV sync thread. Basically wakes up, takes everything that's on the KV queue, and it puts it on the KV committing list and the submitting list. It sort of copies. I think that they appear in two different lists. And then it will most of the time it'll do a flush on the block device to make sure all of those asynchronous IOs that were sent to disks and said they were completed, make sure they're actually committed durably to storage. It'll block waiting for that. Once that happens, then we get a handle on the transaction. We iterate over, this is for updating those IDs, it's sort of not interesting. We updating all these committing things, we go through and we actually give them to RocksDB. I think it's this TXT 5KB that's actually doing that. That's why it was, no, it's not, where is it? Somewhere in here we're actually calling, I don't remember where it is. Oh, maybe we're making a list, I can't remember. Hold on. Okay, so we have sort of one transaction that's our sort of sentinel that's going to push this whole batch through. For each of these, it's queued, then we release our throttle. We adjust extent balancing with BlueStore. We clean up deferred keys. And then finally down here, we synchronously submit the database transaction. So somewhere up here, there's another submit that's not blocking. I'm not really seeing it right now. But then basically, we basically have this whole batch that's all ready to go, and then we push the whole thing through with one that actually has the flag that says RocksDB, you should write this, flush it to disk, and wait until it's actually durable. So this blocks, does a whole bunch of work in RocksDB, and when it finally returns, then that whole batch is committed. And here we basically take all of those lists of transactions that we had, and we hand them off to a new set of lists that have yet another thread is going to mop up at the end. This is one of the performance things that happened over the last year. A little bit better performance on SSDs if you sort of separate the part that's pushing to RocksDB and then sort of doing the after effects. So this pushes it all into these new lists called committing to finalize. And down here, there's the finalize thread that wakes up for all of these things that just got finalized. It calls, it asserts that it's in the submitted state. They should have just been submitted. And then we call state proc. Back over here. Transaction is still working its way through. where is it, submitted. We did it. Calls a little helper txc committed kv that basically triggers the finishers. It queues the finisher work associated with that transaction, updates some stats, and then we're now in the kv done state. And then we go to one of two ways. If there was deferred IO, which means that the original transaction basically journaled an entry that says I'm going to do some IO later, and then it committed. Now we can actually do that asynchronous IO. If that's the case, then we put it on the deferred queue, or it's just a whole another work queue of all that deferred stuff that gets batched up and pushed out. Otherwise, we go straight to finishing. And in the deferred, I'm not going to go into that right now, but in the deferred work queue, basically, similar thing where once we clean up, blah, 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 we get pushed into finishing state. And it's the same thing with finishing where kind of like with the IO, it might be out of order. We might have one transaction that doesn't have deferred IO, another one that does, and then another one that doesn't. We don't actually clean all these transactions. We clean them up in order, and so we have to wait for the slowest one, which might have deferred IO that has to finish. But notably, the things that happen in finish are we mark the write complete, so those buffers states change from writing to clean. We finally mop up the collections that sort of got deleted, if there were any deleted. And then if I'm remembering right, there is one other interesting thing here. This is some trickiness to wake up the deferred IO because it's trying to batch the deferred IO up, but we have to make sure it doesn't stall if there's something that's going to get blocked. And so there's some sort of delicate dance to make sure that we don't stall if we are plugged. But the main interesting thing that happens at the very end here is that if there's any allocations that are released, it happens at the very, very, very end. We finally tell the allocator, in-memory allocator, that these extents are available again. Somebody else can go write on them. This used to be done quite a bit earlier, but we pushed it back at the very, very, very end because there were some really crazy race conditions that could happen where we would overwrite data that hadn't fully been dereferenced yet. Because the deferred IO might have been on an extent that later got deallocated, and so we want to make sure that we deallocate in order after deferred extents IOs are actually completed. And that's it. Again, stuff to make sure the deferred IO queue doesn't stall. Zombie sequencers are sort of one annoying thing where you might have a collection 1.2 or PG 1.2, it gets deleted, and then the OSD recreates the same collection, but maybe the one that was deleted had a bunch of deferred IO that was sort of, even though the transaction that deleted the connect collection finished and completed and the OSD says it's all done, it's actually like still doing a bunch of work. If you reinstantiate that same collection, we want to make sure that we use the same sequencer so that the ordering is all correct. And so that's what the zombie ones are. If the collection gets recreated before all references to it have basically drained out of the system, then we'll sort of resurrect that sequencer. So that's the whole transaction workflow, which we managed to do to mostly fill an hour without actually looking at write. That actually does all the craziness. So any questions before I jump into that?
So I saw we have these perf counters being updated throughout this path in the log state latency calls. Where do we usually see the latency, the most latency from among these steps?
Right. Yeah, and actually you can look at these if you do the Ceph daemon perf command on an OSD. There's a whole BlueStore group, and I've called out the ones that are the most interesting. So let me look at the actual states so I can remind myself. I'm not remember. So AI08, there's going to be some latency there. KV queued, there's going to be some latency there because basically there's the KV sync thread is one thread that's just taking batch, committing it, take the next batch, committing it. And so however long it takes to commit the current batch, depending on how big it is how long, up to how long the next set of transactions might have to wait before they can get queued. So the average latency is like whatever half that time interval.
Right, right.
And then there's also some time it's submitted and then done. If you look at, let's see, up at the top here where we initialize our perf counters, let's see if we can get builder. We can look here at the ones that I called out as interesting. So KV flush latency is how long in the KV sync thread, how long this initial flush is taking. So before we actually even submit the key value data, we have to do a hardware flush on the device to make sure everything is stable. So it's how long that is, basically. And so that'll vary depending on the type of SSD or hard disk. Hopefully it's small. On a hard disk, it'll be big. And then there's the commit latency, which is basically how long it takes for this batch then to actually be committed to RuxDB, which is for the next phase of the KV sync thread. And then the sync latency, I can't remember exactly which part that is. I don't know. I think there's one of them that is sort of the whole span, and one of them, and others are sort of narrowing in on this just on the KV sync thread, and I can't remember exactly how they go, unfortunately. To look at the code. But yeah, there are a bunch of these. Oh, and then how long we're waiting, average AIO wait latency. The numbers are mostly pretty small on SSDs, but on hard disks they can be pretty interesting. The other ones that come up actually are the throttles. So we also measure, remember in queue transaction, we might throttle because the BlueStore has a lot of work or whatever. There's only so much IO that will allow to happen in flight. So we measure how long a transaction that's trying to be queued by the OSD is waiting before it even just gets into the queue. So there's a submit throttle latency. The overall submit latency is everything on the top half where the OSD is doing the work of queuing it. Submit latency is the overall, I think, measurement of the op from submit to commit. And then we measure read latency. And there's a bunch of stats for like, hit rates on the onode cache and buffer cache, how much time we're spending compressing and decompressing or checking checksums, how successful the compression is actually being, and so on. So there's a whole bunch of stuff. Okay, so let's look at do write, because that's sort of the last piece, and it's kind of nutty, but this is most of the interesting transactions actually write data, and that's where a lot of the complexity of all this stuff falls out, because we have to wait for AIOs and deferred IOs and so on. So in do write, if we're lucky, we're not actually writing anything, but usually we are. Choose write options fills out this write context. Just let me look that up. So whether or not this write is going to be buffered, whether we're going to write into the buffer cache or not, whether we're going to compress it, how big we want the blobs to be, how big we want the checksum chunks to be. They can vary on a per write basis because they vary per pool. You can have pool settings that specify whether this pool is compressed or not. It can vary by IO because you might have hints. So for example, Rados Gateway will hint that most reads are large and sequential, and writes also. And so we'll make big checksum chunks that will use less metadata, because usually you don't have to do a very small read and you wouldn't have the read amplification associated with that. So we choose the options. We make sure that the extent map has all the relevant extents for the onode in memory. We actually do the data right. We allocate. Oh, we do a bunch of stuff. Okay, let's go through. So first part, do data right. Do write data. this is sort of the preparation stage. So any write to an object, there's going to be an alignment to the min-alloc size. And so for any write, there's maybe a small piece at the beginning that's a partial allocation unit. There's a part in the middle that's a multiple of allocation units and aligned to those. And then there's maybe a little bit at the end that's also not aligned. So that's the head, the middle, and the tail. And so we have two helper functions, do write small and do write big. We do small writes on the little end bits and then do write big on the big part in the middle. Do write big is nice and simple because we're writing full allocation units, and so we can just write to a completely new part of the device, doing copy on write or whatever you want to call it. We'll just write to a newly allocated region. So we throw out the old extents that reference that part of the object. We're going to allocate a new set of blobs. We're going to loop over the length, figure out how big this blob is going to be based on the max blob size or however big of a write we're doing. If we're not compressing, then, well, there's some complicated bits here because we try to reuse old blobs because it saves a lot of CPU. So the code is kind of complicated here. And I don't understand it super well because Igor wrote it. But the short version is that if it's a new extent, for those big writes, we just write to new space and we'll create new blobs in sort of the general case, assuming you're not reusing. Where that actually happens is we create a new blob, we set new blob to true, and we call write context write. So back in the header, you'll remember this write context had all the settings for how we were going to do the write. It has a map of write items, which are the blobs that we're touching, and flags about them, whether they're compressed or not, and so on. And so there's this write method that basically just puts it into this writes map, which is a vector of all the writes that we're doing for this transaction. Boom. So that's do write big. Do write small is a lot more complicated. Go through it kind of quickly because we can't get into all the details. But basically it tries to do. See if I can remember how this works. It looks at the existing extents and it tries to reuse them. And if it can't, then it sort of allocates a new blob that layers over it. So if there's an existing, this just says there's an existing blob for this sort of region of the object that we're considering. And, if it's immutable, if it's not mutable, then we can't do anything with it, blah, blah, blah. But sometimes it's a blob. Say the blobs are, say the minimum allocation unit is 64K, and we only wrote 4K into it on the last write. And so the other 60K is unused, then do small write will come back and it'll say, oh, this blob is still mutable, and it hasn't been used in this other region that I want to write into. And so I'm going to write into an existing blob, an unused portion of an existing blob. And so that's what one of these cases handles right here. Direct write into unused blobs of an existing mutable blob. And so there are a bunch of conditions that says when that's actually true. And if so, we'll pad it and write it into the buffer cache and do all that stuff. Update the checksum. Dirty blob is a helper that returns a reference to the on-disk structure and sets the dirty flag at the same time. So and it's non-const, and so that we can then call something that actually modifies it, like updating the checksum. And then we set the extent that maps to that updated blob. And we mark it used now, and so on. So the next time this happens, well, it'll be an overwrite, and we can't do this right into unused region. Sometimes we're writing into a blob, but we don't. We need to read something in order to do a read modify write. So when that happens, we figure out what we have to read. And somewhere in here, we actually call to, I can't remember where it is. Somewhere in here, we actually call do read right here. We might actually have to read in the old blob so we can overwrite one byte in the middle of it and then queue it out to write again. So sometimes this will block, kind of annoying. But again, there's all sorts of complicated padding and whatever. This was painful code to write and debug. It's quite stable now. Again, we try to reuse blobs. This is the thing that Igor did that saves CPU, but it's an optimization. But if all that stuff fails, then fine, we'll just allocate a new blob. So say this region is a shared blob that was cloned, and so we can't modify it. We can't do anything tricky to fill it in. We just have to allocate another blob that's sort of logically layered over it in the extent mapping. So we allocate a new blob. We write, we punch a hole. We write into it, and it gets added into the extent map pointing to that new blob. Right. So that basically, so far we've gone through and we've built out this write context with all the writes. The next step is do alloc write. Actually allocate space and sends it to disk. So what happens here is we go through all these writes and we say, wait a sec, should we compress them first? If so, then we figure out what the compressor handle codec is with our checksum compression. If we need to compress, then we compress all the pieces, figure out how big they are, allocate a bunch of space. If we're not compressing, then we already know how much space, so we can sort of skip all the way down here. We allocate space to write all this data, and then we actually finally go to the writes and we actually can write it. And we, in this stage, we calculate checksums here, figure out what the checksum order is, checksum length, initialize checksums. If it's a new blob, we have to initialize a little vector that holds all the checksum values. What does this do? This is building up the vector of extents that we're writing into. We mark them as allocated in the transaction context. Can't remember what dblob is here. I think it's adding a reference to it. We calculate the actual checksums and store them in the blob. We update the extent map to point to these new blobs, and we write into the buffer cache. We do this unconditionally, even if it's not a buffered write, because we have to track in-flight IOs buffers that are on their way to disk in case we modify them again or we read them. And then finally, we queue the IO. This is actually queue it all the way. It puts it on the, what is it? It's calling up. Get deferred up. Oh, this is deferred IO. That's something else. Yeah, normally we call bdev AIO write, which doesn't actually queue the write yet. It's just putting it on this IO context, which is describing all these AIOs that are going to happen. Right. And then finally, that do write is going to call write context finish. And this is going to say all the old extents, I'm going to update the stats for them, deallocate them. Maybe I'm going to share in the EC case for the optimization. But at the end of the day, yeah, it's doing some old extent cleanup mostly. But yeah, write context finish, it updates the inode size. This garbage collection stuff is to basically make it so you don't have too many layers of blobs layered on top of each other. Getting a really complicated map, it collapses them down once it gets inefficient. But it's also complicated, so we won't go into it right now. At the end, we finally update the extent map. We dirty it. I think this compress extent map is, what's that do? Oh, it's basically saying that if you have two extents, say you wrote 4K and it ended up in this blob, and then you wrote the next 4K, and we ended up writing into the same blob because it was unused, and so we took that efficient path and do write small. then you'd have a second extent that points to that same, the adjacent thing. Compressed extent map just walks through the extent map and looks for contiguous adjacent extents pointing to the same thing and turns it into one reference, so the data structure doesn't get too wonky. That's all. But that's it. At the end of this whole process, then we have a bunch of IOs that are described in that IO context, and we have ONode data structures in memory that have been modified, and ONode extent map records that have been modified, and all the blobs that hang off them. They've all been modified in memory. And you'll remember in Q transaction, after we've done this for however many writes we have and all the other random stuff, we finally do write nodes, which prepares the key value operations that actually write that to RocksDB. Finally, where it in gets prepared to the next stage and then finally gets committed. That make sense?
Yeah, I think that makes sense. The garbage collection phase is, I know it's complicated, but it's only for compressed blobs that we are trying to.
Right. Yeah. Yeah. Exactly. Compression. You can't modify a compressed blob because it's compressed and you don't know where the data is and you can't take it apart. It's all sort of one big lump. And so you end up with, if you're doing sort of random overwrites with compression turned on, you end up with blobs that are layered over each other. And so the garbage compression code tries to count for how much space is wasted, basically, in these layered blobs. And whenever it crosses a threshold, then it basically just reads them in and recompresses it and writes it out as a new blob. And it does that as part of the write path. And so there's always a bound that's enforced. There's no like background activity that cleans it up. It's like once you do the third write that's layering over, it does the work of reading in and putting back in an efficient order.
Yeah, thanks.
Garbage collection might be sort of a misnomer there because it's not background.
Mm-hmm.
I think the last thing that I didn't really mention was the deferred IOs. So one of the cases in do write small is if I'm overwriting a blob, either a small piece of it or even just a small, if I'm overwriting a part of an allocation unit, then instead of creating a new blob, we should overwrite the existing one, but we can't overwrite it before we commit the transaction, or else we might corrupt the old data before we commit the new operation. So we have to commit the operation with a promise that we're going to overwrite it and then overwrite it after. And so that happens in here.
We do that for any time we're going to overwrite an existing blob, it's going to turn into a deferred write?
So it's anytime you do a write that's smaller than a block, then it has to do a deferred write, unless it's like a new object and you're not actually touching anything that was there before, because we can just zero around it. But if you're overwriting existing data in a sub block size, then it has to be deferred. If you're overwriting a blob and you're smaller than the checksum, no, it's actually just anytime you're smaller than the blob, then you have to do a deferred write. The exception is that if the blob was not completely written before, like it's a 64K allocation unit, the first 4K is written and the rest is unwritten, and we sort of track that state in the blob, then you can write into the unused portions. But assuming it's been written before, we can't overwrite it until we commit first and then do a deferred write. There's one other case where we do deferred writes. There's a tunable called like min deferred write, I think it is. And the observation was that like 4K, or no, 64K, basically small IOs on BlueStore ended up being slower than on FileStore, because once we hit the allocation unit, we sort of were always writing to new blocks on disk, which meant that for a write, the latency was do the IO, wait for it to complete and flush, and then commit the transaction, and then wait for that to complete and flush. And for small IOs, it's actually faster to just write something into the database that says this is a transaction and this is the data that I'm going to write, and then asynchronously go write it, because the deferred writes get batched up, especially if they're sequential and they get like pieced together into one big I/O. So if you're doing like 4K sequential writes, for example, this will do a whole bunch of, each one will have a transaction to the database that'll commit and come back and batch up all these deferred writes. And then once the batch gets big enough, they'll all get flushed out sequentially. And so it helped a lot for small sequential IOs on hard disks do that.
Okay.
So sometimes we do deferred write even if we didn't really have to, because it wins. And sometimes it's even faster on SSD. I can't remember. There's some, if you just like play with the values, you can like decide when it's, it doesn't seem like it should, but I seem to recall that in some cases it actually helped.
But so in the general case, that like an RVD random workload with a 4K malloc size is going to result in deferred writes all the time.
Yeah, yep. But that's actually mostly a good thing because each IO is basically going to go into one of these transactions to RocksDB. Adding an extra, the actual 4K into RocksDB is not that much additional work because it's a hard disk. It's already writing a big blob to the RocksDB log.
Mm-hmm.
And then they'll go into the deferred batch, which I can show right here, which is basically a whole bunch of deferred IO buffers and locations. We put them in a RB tree, and so they're sort of ordered by where they're going to go on disk. And then when the batch gets big enough, either there are too many things or whatever, then we finally flush it out. Then we put all the contiguous ones together. And even if they're not contiguous, we'll submit them all together, and so the disk can get like this big chunk of IO that they can do a sweep across the disk and do a bunch of like disparate writes without jumping back and forth between the journal and the data area and the journal and the data area, whatever.
That should make it a lot better, especially for the setup where you have SSD for the database, right? Hard disk
Yes,
for the...
exactly right. You get back the benefit that you had with file store where all the IO went to the SSD and was on blocking, and then you sort of lazily flushed it all onto the hard disk.
Right.
You get back that behavior, but with a lot better better design, a lot more control. Because you can still read all that deferred IO is in memory. So if there's a read, then we can actually not non-blocking satisfy that read, whereas with file store we had to like flush the deferred IO to the disk and then read it back from the disk again, which was like super stupid.
Mm-hmm.
Yep. All right. That's probably enough for today. Any other questions on writes? I guess the only other thing to keep in mind is that there are always two batches. So there's the deferred batch that we're building of deferred IO, and then once we submit that batch, then there's another one that you're building while you're waiting for that old one to go to disk. But yeah, that's it.
All right, great.
All right. Thanks, everyone.
Thanks.
Have a good evening.